Hello everyone, today we are going to learn about complex numbers, which are absolutely essential in quantum computing. Quantum states, probability amplitudes, interference, all of this use complex numbers. So, if you ever feel complex numbers are abstract or pointless, quantum computing will finally give them meaning. A complex number is simply a number that has two parts. A is the real part, written as real part of Z, and B is the imaginary part, written as imaginary part of Z. And I is the imaginary unit defined as I equals root over -1, or you can say I square equals -1. Both A and B are real numbers. Any real number can be written as A plus 0i, and any purely imaginary number can be written as 0 plus bi. In classical probability, everything is real numbers between 0 and 1. But in quantum mechanics, the state of a system is described by probability amplitudes, and these amplitudes are almost always complex numbers. For a qubit, their magnitudes determine probabilities and their angles or phases determine interference. Now, think of a complex number as a point in a 2D plane. The real part is the horizontal coordinate and the imaginary part is the vertical coordinate. So, z equals a plus bi is the point AB on the complex plane. This geometric perspective is extremely important because quantum states also live in a kind of complex vector space. Now let's see how to add, subtract, multiply and divide complex numbers. These basic operations show up all the time in quantum computing. In case of addition, just add the real parts and the imaginary parts separately. Do the same thing for subtraction. For multiplication, we use the distributive property, and remember that I square equals -1. To divide, we multiply both by the conjugate of the denominator. Here, the conjugate of c plus di is c minus di, and the denominator becomes c square plus d square. So, the denominator is always real. Now, what is complex conjugate? The conjugate of a complex number simply flips the sign of the imaginary part. So, if we have z equals a plus bi, then the complex conjugate of z will be a minus bi. Conjugates are essential in quantum mechanics because inner products use conjugates, probabilities require multiplying by conjugates, norms of quantum states use conjugates. For example, we can write, and this will be always a real number. The magnitude of a complex number is just like the length of a vector. For z equals a plus bi, we can write the magnitude like this. In quantum computing, the magnitude of a complex amplitude corresponds to probability. One of the most critical concepts in quantum computing is phase. Every complex number can also be written in polar form like this. Z equals r into e to the power I theta, where r is the magnitude and theta is the phase or the angle with the real axis. The phase controls quantum interference. Quantum gates like phase gate, T gate and S gate modify these angles. Now, before we go to the lab, remember few things. A complex number has a real part and imaginary part. Complex numbers behave like 2D vectors. Their magnitude gives probability in quantum mechanics. Their angle or phase gives interference effects. Alright, now let's switch to the practical part. Open your Google Colab notebook and we will start experimenting with complex numbers directly in Python. The good news is Python has built-in support for complex numbers, so we don't need any extra libraries. Now type this, z1 equals 3 plus 4j and print this. Notice that Python uses j instead of I, but it means exactly the same thing. Here 3 is the real part and 4 is the imaginary part. So 3 plus 4j is the complex number 3 plus 4i. Now let's create another complex number z2 and print it. Python gives us built-in attributes like .real, .imaginary. Now write with me. For Z1 you should see 3 and 4, and for Z2 you should see 1 and -2. This matches exactly what we expected. Now let's perform the basic arithmetic operations that we discussed. At first add Z1 and Z2, then print the result. Now perform the subtraction. Now multiply Z1 and Z2. Similarly, perform the division and print the result. Okay, now we have completed all the basic operations, and remember one thing, Python handles all the real or imaginary separations and uses I square equals -1 behind the scene. Now find the complex conjugate. To get the conjugate, Python gives us a dot conjugate function. So this simply flips the sign of the imaginary part, exactly as the math says. Now let's compute the magnitude or the length of a complex number. This is super important in quantum computing because the magnitude of a complex number tells us the probability. At first, do it manually. Now you need to know that in Python this double star or double multiplication operator simply refers to power operator, and something to the power 0.5 simply refers to a square root operation. Now let's compute the same magnitude using NumPy's built-in function. You can see the both results are exactly the same. Now let's do something that connects directly with the quantum state. Let's create something that looks like the amplitude of a quantum state. Let alpha equals 0.6 plus 0.8 I. The magnitude should be root over 0.6 square plus 0.8 square, which must be 1. Now try this with me. Both results should give you exactly 1, meaning the complex number has unit length, and in quantum computing, a valid state must have total magnitude or norm equals 1. So you are already working with something that behaves like a quantum amplitude. Remember that if a quantum amplitude is A plus Bi, then the probability is A square plus B square. Now let's compute that. This gives exactly 1. because 0.6 square plus 0.8 square equals 1. So, if alpha represents the amplitude of 0, then the probability of measuring 0 would be 1. In this lab, you learned how to create complex numbers, how to access real and imaginary parts, how to perform addition, subtraction, multiplication and division operation for complex numbers, how to compute magnitude manually and using NumPy, how to get the conjugate, and how to connect complex numbers to quantum amplitudes. And that's all for today's video. Hope you liked this content and understand it properly. In the next class, we'll discuss about probability. Make sure you subscribe the channel and like the video and share it to your friends who are also interested in quantum computing. See you in the next video. Until then, happy quantum computing.